Welcome to watching this video. This is Longwing Science and Technology Corporation. Today the topic is about measuring thermal resistance and conductivity of thermal interface materials, TIMs, based on ASTM D5470 standard. Now we'll briefly introduce the test method, which is ASTM D5470-16. This is the standard test method for thermal transmission properties of thermally conductive electrical insulation materials. And 16 actually means 2016. So this standard was published in 2016. And here, the so-called thermally conductive electrical insulation materials are considered as thermal interface materials, aka TIMs, which are generally applied in IC package and electronic cooling fields. TIMs include thermal grease, thermal paste, phase change materials, thermal pads, etc., which are used to minimize the contact thermal resistance or thermal impedance across interfaces. There are many ways to measure the material's thermal conductivity, but actually this one, ASTM D5470, is the most suitable to test the interface material because we can see the actual application scenarios by using this method. And for your notice, ASTM, the full name, is American Society for Testing and Materials International. And in this slide, we can see different types of thermal interface material, such as grease, and also a thermal pad, also like a thermal tape or the MCPCB board. And this is the outline for today's presentation. First of all, we'll provide a detailed definition of thermal resistance and thermal impedance. Second, about thermal conductivity. Third, we'll move on to contact thermal impedance. And the second part would be how to test thermal resistance. And the third part would be the standard ASTM D5470. And the fourth part about the applications of this standard. And the fifth part will introduce Longwing's product, the TIM tester. So for the first part, we'll go through the definitions of thermal resistance, thermal impedance, and contact thermal impedance. Now we'll take a look at the definition of thermal resistance. When a high temperature A transfers the heat to the low temperature point B, in this path, the resistance existing, that's so-called thermal resistance. When the thermal resistance is lower, that means the heat is easier to transport. And the definition of thermal resistance is the temperature difference divided by the power dissipation. If the temperature difference is the same, but with more power dissipation, that means the lower thermal resistance. Or the power dissipation remains the same, but the temperature difference is lower. That also means the thermal resistance is lower. And on the figure of right-hand side, this is the formula of electrical resistance. And you might be wondering why we put electrical resistance and thermal resistance together. Because when we are in the high school, we learned the definition of electrical resistance, and we also learned the correlation of putting the electrical resistance in serial or in parallel. So actually, when we are analyzing a complicated thermal dissipation system, we can also consider it as in serial or in parallel correlation, and we can analyze the heat dissipation performance of each section. Now we'll take a look at the cooling module of a laptop computer, and we can take a look at how the heat transfers through this module. You can see from here, this is the chip. This is a chip, and also the CPU where the heat is generated. And then the heat will pass through the TIM material, such as the thermal grease, and pass through the copper plate, and then the heat pipe, all the way to the fin. And then there's a fan, and then the wind will dissipate the heat away. And we can also draw a schematic drawing of this cooling module. And we can take a look at how the heat is transferred. You can see the part in red. This is the hottest spot of a chip. And the part in pink, this is the thermal interface material, could be a thermal grease or thermal pad. And the heat passes through the gray part, which is the heat pipe or the cooling fin. And then the fan will blow the wind and dissipate the heat to the ambience. So here we can see from the right hand side, this is how the heat transfers, just like the electrical resistance put in series. So from the junction temperature to the block, or we can say the lid of the CPU, all the way to the heat pipe, and then to the fin onto the ambience. Every section owns its own thermal resistance. And for thermal engineer, the main target is to make the total thermal resistance as low as possible, such as we can increase the flow rate or improve the thermal performance of the heat pipe, or we can also improve the performance of the cooler or the heat sink. Also, we can try to improve the performance of thermal interface material, because the thermal resistance is effective in series connection. When the thermal resistance of the interface material is big, even though others' thermal resistance are low, that will not help the system much. So during this analysis, we'll need to know the bottleneck of the whole system, and we have the goal to decrease the overall thermal resistance. So here we can see some formula about thermal resistance and thermal impedance. Actually, there are two ways to describe thermal resistance. The first one is so-called thermal resistance, and the second one is thermal impedance. And you can see from this slide, they have different units. And the key point is, if you want to compare the thermal resistance, you need to consider thermal impedance, because thermal resistance would be different when the heating surface or heating area is different. For example, the same material, when it was put on the on a heat source with 20 times 20 millimeter, and another one put on the surface 40 times 40 millimeters. The area, if the area is bigger, the thermal resistance will be smaller. So if you want to compare the thermal performance of a material, an area unit must be included. So the thermal impedance equals to the thermal resistance per unit area. And we'll continue to figure out the correlation between thermal impedance and the thermal conductivity. From the second formula, we can see the thermal impedance is equal to the thickness of the thin material divided by the thermal conductivity. If we want to improve the thermal impedance, which is making the thermal impedance lower, we can increase the thermal conductivity or decrease its thickness. If you want to have a good thermal performance, we need to decrease the total thermal impedance. Another thing to consider, thermal conductivity is the property of a material. Take copper as an example, which thermal conductivity is around 400 watt per meter per Kelvin. No matter the thickness or the dimension it is, and these factors will not change the thermal conductivity. However, thermal impedance or thermal resistance will be varied with different thickness. If the material is thinner, that means the thermal resistance or thermal impedance will be lower. In this slide, we are going to take a look at the contact thermal impedance. So you can see there's a schematic drawing. When the heat transfers from material 1 to material 2, in this path, you will see the surface of these two materials are not perfect. So we need thermal interface material to fill in all these gaps. And the overall thermal impedance will include the contact resistance of the two interfaces and also the resistance from the thermal interface material itself. If we analyze it further, the factors of total thermal resistance include the thermal conductivity of the thermal interface material, the thickness of the thin, and the two contact resistance. In total, there are 3 factors. So we need to consider it as a whole system, because if we just want to increase the thermal conductivity of the tin, but on the other hand, we increase the contact resistance, which is not a good way to solve the issue. Take copper as an example again, which thermal conductivity is around 400 watt per meter per Kelvin. And the thermal grease, the conductivity is much lower, usually around 4 watt per meter per Kelvin. And why don't we use the copper as the tin and we just use the thermal grease? Why? Because the thermal resistance actually is the key factor in this scenario. So here we can see the highlight sentence. The thermal conductivity of thermal interface material is not the only factor that affects total thermal impedance. This is the second example that we can see the combination of thermal impedance. Here we take the